Good morning, students. So we'll begin with a new chapter, that is assembler. Fine. So from this chapter, we'll be knowing like what is the job of assembler. So what are the internal procedures getting involved to convert assembly level language into machine level language? Means source program to object program. Fine. So here we need to discuss very important concept like uh, what is the object code exactly, or object program, how it look like exactly, how many different parts are available in this object program. Okay, first we need to discuss about that. Later we need to go for pass one algorithm and pass two algorithm, okay, using which how we can convert the assembly level language into object program. Okay, so this chapter is entirely dependent on assembler. Fine. And one more thing I would like to inform you in the beginning itself, we are not discussing about SICK XC machine architecture, the concepts of assembler. We'll be discussing about SICK, the basic version of machine architecture exactly. Based on SICK, we'll be having the complete programs or the logic or the work examples. Okay, fine. So first, what exactly assembler means? An assembler is a program that converts an assembly language program to its equivalent object program. Now, what is this assembly, or what is like assembly level languages we are calling it as? See, in previous lectures, we were discussing about few programs. Is it right? Like store accumulator, okay, space length. Fine. In this, store ST stand for what? Store the content which is residing in the accumulator to a destination called as a length exactly. Okay, so such type of mnemonics will be used, such type of assembly language mnemonics will be used for writing the programs. Yeah, okay. When we are comparing it with higher level languages, okay, like C program or C sharp or else Java, JavaScript and all, okay, if you read that particular sentence or if you read that particular line of a code, you can identify, yes, this is going to happen. Okay, but here, like sentence kind or the words we are familiar with, that will be used over there in case of higher level languages. Okay, but in case of assembly level languages, we'll be working with a bit lower level. When we are comparing it with the higher level source code, okay, assembly level code will be bit lower version exactly. Means like it will be completely written by utilizing the mnemonics. That's it. Okay, like move it maybe for adding a two number, you used to write a plus b, right? Okay, but here you need to write like a add a comma b exactly. Such type of programming languages we will be utilizing. But for converting such type of programming language into a object program, okay, that is machine level program or machine level code, okay, we need to dependent on a assembler exactly. The job of assembler is converting assembly level language into equivalent object program exactly. Okay, fine. So how it is going to be done? Okay, we'll see. The assembler accepts a source program written in assembly language as the input and produces object program as the output. Fine. So assembler, okay, is just like a junction who is receiving the input called as what? Assembly language. Okay, that is what the program, the source code, okay, which is written using assembly level language. And the output of assembler will be what? The object program. Remember, this is not the final output for that particular program. Remember this. We are just having the conversion of a language from the source program into object program. That's it. That is what the conversion. Okay. Now, later, this object program should be processed by your system or processed by your processor exactly. We'll see that. Okay. What is the job of this object program, or how this object program will be utilized in further? We'll see that. The object program consists of, very important thing it is, the object program consists of two aspects. Okay. One is what? The object code. Okay. We are calling it as what? One is what? Object code will be utilized, or object code will be specified, okay, which are nothing but instruction given to the microprocessor. Okay, object program is residing with the two aspects. One is the object code, that is nothing but it is an instruction for your microprocessor that what should be done. Okay, whether you need to add the two variables or whether you need to add the two operand, whether you need to shift the content of one memory location to a register or register to memory location, such type of instruction will be available inside object code exactly. Okay, second thing, it also contains instruction to the loaders. Okay, so we'll see what exactly loaders are and linkers are in module number 2 exam. Fine. Okay. For time being, we will be stick on to the point number 1. Object code is considered. Object code means what exactly it is for an instruction for the microprocessor exactly. What kind of instruction, how it will be given in the will see that. Okay. So I hope you don't have a doubt regarding the assembler. Assembler means what it used to accept the assembly level language. That's it. Okay. It will convert its equivalent machine or else we are calling it as a object code exactly. Fine. Okay. So that is the concept of assembler. Now, basic assembler functions. Fine. What is the main function of our assembler? We'll see this. First function is translating mnemonic language code to its equivalent object code. So this will be the first basic function of the assembler. Okay. Whatever the mnemonics we are available with, that should be converted to an object code. Okay. Second thing, assigning machine addresses to symbol or symbolic labels. Okay. See, in this assembly level language, we are using some shortcuts or we are using some keywords to identify or to specify the instruction which we need to provide it for the microprocessor. Along with that, okay, we are using some memory location or we are using some labels, okay, of a memory location to identify a particular location and to target some operand residing that exactly. Okay, so such type of labels if you are using, example, we have a location called as 1000. Okay, I'm labeling it as a start. In my entire program, I'm not going to target that particular 1000 with a address called as 1000. Okay, I will be targeting that 1000 based on the label itself. Okay, what is that label? Start exactly, right? So while converting assembly level language into object code, such type of label, if it is available, that should be replaced with its machine address. Remember, whatever the address is assigned for that particular label, okay, so that should be replaced exactly. Fine. Okay, so here we have a pictorial representation like source program, that is nothing but the assembly level language, okay, will be provided as the input for the assembler. Then that assembler will be generating the object code. So this object code will be in the format of like in our example, we'll be utilizing the hexadecimal series of numbers exactly. Okay, that indicates some object code representation exactly. We'll see that how it can be done. Okay, the design of assembler can be to perform the following. Okay, so assembler should perform certain job. Okay, so we'll see that what are the different jobs should be performed by the assembler. Okay, first thing is what? Scanning. Okay, first we need to scan entire program. Okay, and we are trying to categorize them. Okay, so that we are calling it as tokenization or tokenizing. We are calling it. We need to create some token, piece of codes. Okay, piece of code, such type of token we need to create. Okay, so this process will be explaining in deep. Okay, in case of lexical analysis or else a compilation or compiler part exactly. There you will be understanding it in better way. Okay, compiler means what? Which will be like higher level languages, whatever we are learning, right? Okay, so that should be converted to a object code, final destination. But there we will be using the compiler exactly. There, the scanning or a tokenization concepts will be very clear. Instead of discussing in case of assembler, we will discuss in model number 3 exactly. Okay, then later, parsing. Okay, validating the instruction. Parsing means what? Validating the instruction. So whatever the instruction we are using or we are writing in our program, okay, whether it is a proper instruction or not. Okay, see in ATC automata theory, okay, we were having like parse trees, is it right? Okay, and we were checking like ambiguity. Ambiguity means what? For particular condition, there will be a two possibility exactly, right? Such type of possibility will create some confusion for our assembler. Remember this, okay? For avoiding that, what we are trying to do, we are trying to manipulate that condition exactly. Is it right? Okay, to remove that ambiguity over there. Same type of validation we need to perform over there. Okay, such type of error or such type of complexity is available that should be intimated to the user so that we can make some correction in the error and finally we can execute the instruction exactly. Fine. First is scanning the program, parsing the program, validation. Okay, then creating the simple table. This is very, very important. Okay, creating the symbol table. Okay, what is this symbol table? Okay, just observe or just imagine you have a table. Okay, you have a normal table. So in front of that, or else in that table, okay, we are having total 2 to 3 columns exactly. Okay, in first column, we are having the operands, or we are having the labels, whatever we are using in our program. Okay, that will be the first column will be for labels exactly. So in front of that, that label means what exactly? See, in this presentation, initially I took an example like 1000 is a memory location. For that, we are labeling it as a start. Okay, so wherever, okay, we are finding that start, there it should be replaced with 1000 while execution. Is it right? Okay, how it will be replaced? That is what the question. Okay, just because of this simple table example. Okay, so whenever we find such type of labels, okay, appropriate address, whatever we are having, that should be managed in your symbol table example. Remember this. So for managing this symbol table, we are having two algorithms, like pass one algorithm and pass two algorithm, or one pass and two pass we are calling it as. First, we need to scan, we need to identify few such type of labels, okay, and in front of that, what is the particular address? Okay, that should be specified exactly. But here, remember, sometimes, okay, the labels which we are using, okay, in the initial portion of the program, may be defined with the address later exactly. Right now, you may not be available with the original address of that particular label, but we are utilizing. Fine. So during that, we may be finding a problem to identify what is the particular address of that label itself. So what we need to do? We need to go for second scanning, or else second pass we are calling it as. Okay. Such type of like next point we are resolving the forward reference. That is what the forward reference we are calling it as. Means you are in a line number 1000. Okay, you are using some label over there. Okay, but you don't know what is the original value of that label exactly. That original value of that label, feel that it is specified in 1050 location. Okay, but you are in 1000 exactly. You don't know what is 1050, right? So during that, we are not providing any kind of a address for that label. We will keep it as blank. Okay, but during the second pass, okay, like after 1000, we'll be going for 1003, 1006, 1009, such type. We'll be coming to 1050, right? When you are reaching the 1050, you will get to know, like, or your assembler will get to know, like, yes, this particular label means 1050 exactly. Okay, then during the second pass, again we are coming from the starting, okay, for the symbol table, and if you are left with such type of forward reference, that will be overrated. Okay, that will be overrated with original address exactly. So this should be done by your assembler. Okay, then at last converting into a machine language. So assembly level language, whatever we are having, that should be converted to machine language. So these are the total 5 different steps which should be performed by one assembler exactly. Okay, so here we are having a simple SIG assembler. Okay, so as I specified, we are discussing about the SIG machine exactly. Okay, so we'll see what is this SIG assembler job. Okay, fine. The translation of source program to object code requires us to accomplish the following functions. Okay, not necessarily in the order given. Okay, maybe like you may go for different orders, doesn't matter exactly, but we will follow like 1, 2, 3, 4, 5, total 5 different like order we are. Okay, fine. Convert mnemonic operation code to it, code to their machine language equivalents. Okay, see, like such step of like mnemonic operation code we are calling. Here we are having one example. See, store L. Fine, store L. Okay, store the link register. Okay, means whatever the content you have in the link register, that should be stored in some location exactly. What is that location? We don't know. But the store L, okay, can be converted into a machine code, or I'll say object code with a hexadecimal value called as 14. Okay, in case of assembler, 14 stand for what? Store the link register. Okay, that is what the object code for storing the link register exactly. Okay, such type of mnemonic operational codes, example like add, load, okay, store, fine. Other than that, moving the content, okay, any other kind of operational codes will be using in our assembly level language. Such type should be converted, or it should be translated to its appropriate equivalent what machine language code exactly. First thing we need to do. Later, second, converts symbolic operands to their equivalent machine addresses. Okay, say the labels, whatever we are using. See, in case of this, Example, second one, example, translate RETADR means return address it is. Return address to 1033. Okay, means return address is a the operand, whatever we are using in our program. Okay, operand. Okay, so that is defined in line number or else address location called as 1033. Such type of symbolic operands. Okay, I tell you, such type of symbolic operands, if anything is available, so that should be converted to its equivalent machine address. Remember, you may ask why we are writing that return address to 1033. Why can't we write it as 1044 or anything else? Okay, in the next slide we have a program. Okay, so from that I'm taking this example. I will explain why I'm writing return address 1033. Okay, then later, third one, build the machine instruction in the proper format. Okay, build the machine instruction in the proper format. See, in this session itself, we'll be noting that, or we'll be discussing that on what format the assembly level language it should be, or on what format like object code it should be. Fine. Okay. So machine instruction, it should be in a proper format. Okay. Simply we cannot write. Okay. It should be in a proper syntax. We'll see that what is that syntax. So third step. Then later, fourth will be convert the data constants specified in the source program into the internal machine representation. Example, EOF. EOF stands for end of file. If you are trying to read a file, okay, when you are reaching the end, okay, we are setting a code called as EOF. Okay, that is nothing but end of a file. Okay, so such type of constant words, whatever we are using in our assembly level language, remember, see, in previous lecture and all 5, 0, 1, such type of constant value we were using. Is it right? This is not of such type. Remember, so these are all what inbuilt function, okay, inbuilt constant which you are using in your assembly level language. Okay, for such type of constant, we are having a particular hexadecimal value specified, like particular hexadecimal value we are having. One of the examples is what end of file for that 454F46. Okay, so whenever your assembler finds this code like 454F46, okay, then it will be considered as what end of a particular file. Okay, so such type of constants if you are having your program, so that should be converted into its original representation. Okay, then write the object program and the assembly listing. So we'll see how we can write that. So this is what a simple thick assembler used to perform. Okay, so here just observe, I was taking some example of 1300, right? Okay, so return address. Okay, regarding this, I was saying return address means what? Reserve a word. How many bytes? 1 byte exactly. See, these are the what line number exactly, which is having a difference of 5. Okay, but actually, in next line, we are having this observe where we are having a difference of 3 exactly. So here, return address, what I was taking, right? Return address. So this is a data operand. Okay, this is data operand which is stored in location 1033. You can easily identify this. Observe return address where it is 1033 exactly. Such type. Okay, fine. Such type should be end of file means what? Here 454F46 exactly. Okay. So now I want to explain this program exactly. Okay, I don't want to go in deep because that is not necessary for your discussion. Okay, so here we got 3 different programs. Okay, so here we got 3 different programs. Just observe. So this portion we are calling it as a main program. The task is, see here, the task is we have an input device, okay, and we have an output device. Fine. What we are trying to do is input device which is having a address called as F1. Okay, we are transferring it to a output device which is having an address called as 5. Feel that? Okay, this is an example. This is an example. Output device which is having a address called as 5 and input device which is having an address called as F1. The task is what? From input device, the content should be transferred to the output device exactly. Okay, but here we are doing it based on a buffer. Based on a buffer. Okay, and I want to like inform you that so this buffer is having a capacity of 4096 byte. Okay, 4096 byte is the maximum capacity of this buffer exactly. Okay, so now if the input file, whatever we are trying to copy it from input device to output device, if the size of that file is more than the size of the buffer, we are performing it twice exactly. Here, if the input file is less than 4096, then in single attempt we can start reading the content from input device to buffer, buffer to output device exactly. Okay, so this will be coming in this way. Okay, and from here it will be traveling exactly. Okay, so this let me clear the screen. Okay, so this program, fine, this program is the main program. Okay, so this is calling two subprograms exactly. So this is the subprogram to read the record into buffer, just observe. Subroutine to read record into buffer, and this is the subroutine to write record from buffer exactly. Okay, input to buffer, buffer to output exactly. Okay, so here we are using lots of mnemonics available. Okay, see first one like start means what 1000 again. So this is what the first line of the program. Okay, so the program name is, so this program name is copy. This program name is copy exactly. Copy file from input to output. Okay, so that is what the task. So the first line first indicates what this is the first executable instruction of this particular program. Store link register. Store link register with the return address. See here you are at line number 10. Is it right? Okay, you are at line number 10 or some address available over here. Store link register. Okay, fine, no problem. But return address. What is this return address? What you know? We don't know anything. What is this return address? See here, return address is what? A data operand exactly. But regarding that, we won't be having any information. Okay, so during one pass, we are not replacing this return address with the original address of this label or a data operand. We will let it as it is. Okay, during one pass. Okay, but during the second pass, like one by one, we will be processing. Okay, then one time we will be coming for this location. Then we will got to know like what exactly this return address is. Then during the second pass, you will be having a clear information. We will just replace them. Okay, so like that we are having. We will be calling the read program or read content first. Okay, after reading, after uploading it for the buffer, from buffer we are writing it to the output unit exactly. So this program is not much important. Okay, but like what are the mnemonics we are using, what is the work principle of this assembly level language for understanding that this is best exactly. Okay, so the difference between this program and the second program is the program is totally same. Okay, we don't have any difference. Okay, but only difference is what here instead of line number, okay, general line number, this is not compulsory. Okay, location where these instructions are stored that has been given over there. Okay, location of these instructions. First thing is given. Okay, then the same program, main program, read program, write program it is, and appropriate, observe it very careful, appropriate object code. Appropriate object code. Just observe this. I don't want to take example of each and every object code which has written over here. Okay, it will be more difficult to explain each and every, okay, because of scarcity of time. Okay, so we'll take this first one. What is this? Oh, wait, sorry. Okay, so what is this instruction exactly? Store L return address, right? How to convert it for object code? See, these kind of operational instruction, whatever we are having in assembly level language, they'll be having its own hexadecimal representation. Okay, as a machine code exactly. Store L from previous slide we got to know. Store L means what? 14 exactly. So 14 we are having. Then later, in front of that, what we are having, return address we are having. Okay, what is this return address exactly? What is this return address? We don't know what is this return address exactly. Return address, see here, return address is a label or label for a location 1033 inside which is having one word capacity which will be reserved for the further use exactly. Okay, so whatever the value we have inside the linked register L, that should be stored in this particular location. Okay, what is that location? Here 1033. From where I am writing this 1033? From here. Just observe. Okay, what I am trying to do is I need to store the linked register content into return address. But what is return address? I don't know. Okay, so Return address means what? Return address means a memory location exactly. That is a label for this particular 1033. Okay. Then if I execute this instruction, so if I want to execute this instruction, then I need to generate such type of object code that is 141033. It indicates first two will be for what? Will be for operation code. Okay, store the link register content. Where exactly I need to store 1033. That's it. Such type of object code is specified. Okay, so the conversion of this assembly level language into object code, it's a very interesting topic. Okay, but that is not specified in your syllabus right now. Okay, so if we get time in further classes and all, okay, then we will discuss about that. Okay, how this object code, sorry, if this uh, instructions are converted into object code, we'll see that in further classes and all. Okay. So I hope you don't have a doubt in this program. Okay, this is a very simple program. The thing is, we are beginning with the starting line. Okay, the starting line of the record. From that, we will be continuously uploading it for the buffer. Okay, so once we are reaching the end of the file, okay, so that end of the file we are identifying here based on 0 exactly. Okay, like if there is no lines or no input is available for reading procedure, then it will be identified by 00 exactly. So when we find the 00, we feel that end of the file. Okay. So when we are finding that end of the file, we will be starting uploading the content from the buffer to the output device exactly. Fine. So here also the same procedure continues. When you are finding 00, that indicates that end of the file exactly. Okay. Finally, the control will be suspended from subroutine program to the main program. Finally, the content will be displayed. So this is how the assembly level program will be converted to the object program and execution principles. Okay. So now, next. But here, as I mentioned, the problem we'll be facing over here is problem of forward reference. Okay. See, return address. Just observe this instruction. Store a return address. First time we are using this return address, right? You are at the address called as 1000, right? But this return address is stored in 1033. So you have a gap of 30 different address locations exactly. Is it right? Okay. So we are calling it as a forward reference. We are using something in location 1000, but it is defined in 1033. Means forward reference it is. Okay. Such type of problem we will be facing. Okay. Same example I'm taking over here. Okay. To resolve this, we are calling it as first pass and second pass to solve forward reference exactly. Means like while reading, while scanning the program from first line to the last line, if you are finding such type of labels, okay, which is right now it is not defined, okay, so we will leave as it is during the first pass. But during the first pass, we will be scanning each and every line of the code, right? Somewhere that particular label is defined exactly how it is defined in 1033. Is it right? So that time we will be identifying the return address means 1033, and later during the second pass, okay, wherever return address is there, before that we left it blank, right? Wherever return address is there, everywhere 1033 will be placed exactly. Okay, so this is how we solve the forward reference problem exactly. Okay, then later, next, apart from this, we will be having assembler directives. Okay, see, here we are having different directives over here. Okay, see, start we have, sometimes we'll be having end. Okay, so this is type of, we will be calling it as what? Directives. Directives means what? It is a instruction, or it is a direction given to assembler that what we should do when we are getting these kind of things exactly. Okay, so few assembler directives I'm listing over here. One is what? The byte. Okay, byte means what? Character based. If you are trying to deal with only one byte of information, okay, then we need to use a directive called as byte. Okay, if you are using byte with some particular memory location, from that location, memory location, right most one byte will be utilized, or right most one byte will be accessed exactly. But in case of word, the second example, the complete word will be utilized exactly. Yeah, then later, sometimes we need to reserve the bytes. Okay, see, for what purpose we are using these reserve cases is, see, while executing the program, sometimes we'll be generating a few results. Okay, few results. We may not be knowing like what is the original value of that particular operand, but due to the logic or due to the execution, we may generate some result exactly. So that result we may be managing in some location. So that location should be reserved exactly. Remember this. For that purpose, we are using two varieties. One is what reserving the byte, second is what reserving the word exactly. Reserving byte means what? If you are trying to save or if you are generating a character wise, or else if you are generating a 1 byte information as an output, then reserve byte. If you are generating 1 word as an information, then reserve word should be used. Then start and end are the two indication, like from where the program is beginning and where exactly program is terminating. Okay. Then finally, the assembler must write the generate the object code onto some output device. This object program will be loaded into memory for execution. Okay, now we'll see what exactly object program is, how they look like. Okay, so object program format is of total 3 types. One we are calling it as header record, second we call it as a text record, and third one we call it as an end record. Okay, so we'll see what are those. See, before I explain this text record, header record, and end record, I want to show you what is this object program. Okay, so this is what the object program. Okay, see, this is what the object program per line. Fine, so that we are writing in this fashion itself. Okay, per line, whatever the assembler object code we are generating. Okay, so that should be written in this fashion exactly. Same program, not same code. What you are writing individually right there. So this will be in the fashion of header, text, and end. Okay, so we are having some syntax like how header should be written, how text should be written, and how end should be written exactly. Okay, so we'll see this. So header record contains the program name, starting address, and length exactly. Okay, so here we are identifying based on a columns. Column 1 will be with capital H, that indicates it is a header record. Later, column number 2 to column number 7 means 6 different characters are reserved for specifying name of the program. Okay, specifying name of the program. See, the name of this program is what? Copy. Right? The name of this program is copy exactly. Okay, so same example we are considering. So in the name of the program, copy will be written. Then column number 8 to 13, starting address of object program. Starting address of object program. In this example, 1000 is the starting address. Remember, 1000 is the starting address. Then later, column number 14 to 19, length of object program in bytes. Okay, what is the total size of your object program? Okay, that should be calculated. Okay, in case of bytes. Remember, in case of bytes. So these all things should be mentioned in your object code. Okay, I will show you how it is. See, one column, first column we are utilizing it for identifying whether it is a header, whether it is a text, or whether it is an end. Capital H we have. So this is the location for what? Location for identifying or mentioning the name of the program. And this is what the starting address 1000. And this is what 107A. 107A is the total number of bytes. Total number of bytes we have inside this program exactly. Okay, like 2 column we are considering it as 1 byte. 2 column we are considering it as 1 byte. Such type 107A. Okay, number of bytes which is residing in this complete program example. Okay. Then later, so that was regarding the header record. Then text record. This is a bit difficult compared to the header record. It is not so simple. Okay, contains sorry, contains translated instructions. Okay, translated instruction means what? That same object code, whatever we are targeting, that will be available. Okay, data of the program. Okay, so whatever the data we need to deal with, so that will be available in this text record. Then later, together with an indication of the address where they are to be loaded exactly. Okay, so each and every instruction or each and everything will be available in this particular text record. What should be done and all. Okay, so the first column of this text record will be T. This 2 to 7 will be the starting address for object code in this record. Okay, then later starting address will be available. Okay, then later 8 to 9 length of object code in this record. Okay, in bytes exactly. See, this is not the starting address means like from where. Okay, I tell you when they are reaching the last line, I will tell you what is this. The starting address for the object code. Okay, that's better. I will tell you now itself. See, this is the first line. See, 1000 is the first line, right? Okay. From first line to here, okay, we'll feel that we may be including total 10 different instructions. Okay. Then here it indicates that 11th instruction. Okay, the starting address of this particular document. Okay. So if you are considering these are the different documents. Okay, one program but different documents. So in the first line, you will be having the instruction for just of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 different instruction object code we are included. Okay, the first instruction it is and 10 it is. Okay, total. So like that, 11th instruction address will be specified in the beginning. Okay, later just observe. Okay, what should be the next? Length of the object code in this record in bytes. Okay, object code in this record in this bytes. Okay, total 1E is the total length or total number of bytes we are including in this particular line. Okay, so that should be suitable. For this 15, for this again 1E, then again 1C, then 07. So these are the what? The number of bytes we are included in this line exactly. Okay, see, in first line, we are accommodating total 10 different instruction object code. Okay, then the 11, 12, 13, 14, 15, 16, 17, such type will be accommodated in next line exactly. But during that 11th instruction, okay, 11th instruction, address should be mentioned in the beginning exactly. Later, how many bytes you are included in this document or in this line, that also should be identified exactly. Okay, so that is how the text record used to work exactly. Then at last, column number 10 to column number 69, that is the maximum capacity per line exactly, object code represented in hexadecimal. Okay, 2 column per byte, 2 columns per byte of object code exactly. Okay, so 2 columns per byte we can accommodate. Okay, so after this, here end record. Okay, marks the end of the object program and specifies the address in the program where execution is to begin exactly. Okay, so we'll be having only 8 columns, 1 to 7. 7 columns, 1 to 7. Okay, the first column will be identified by E, that indicates that yes, it is the end of the object code. And later 2 to 7, address of first executable instruction in object program. Okay, see, what is the first executable instruction in this particular object program? 1000. Is it right? 1000 is the beginning address exactly. That should be specified in the end also. That should be specified in end also. Remember. Okay, sometimes okay, it will help us to go for the loop. Okay, multiple number of times if you are trying to execute the same program. Okay, then like after executing complete instruction from starting to end, okay, you will be targeted to starting itself. Okay, so here you can observe E, we have E, right? Then followed by 001, 000. Okay, so this is what the object code representation. First will be the header, then later will be the text record, later will be the end record. Only thing you need to notice is header followed by name of the program, beginning line of the program, how many number of bytes we are involving in this entire record. Okay, so that should be mentioned. Then later text record. Okay, it should begin with T. Then the starting line of the particular or starting address of a particular line. Okay, so that should be mentioned. Then later, how many number of bytes you are involving inside this particular line, that also should be included. Then later it will be followed by the object code example. Okay, then later next line, okay, starting address. Okay, how many number of bytes you are involving here. Okay, that should be specified and text record. Like that it continues in there. And these arrow marks, okay, or these indication, okay, whatever we are having, actually won't be available in our original object code, okay, or object program. Okay, this is to just identify, okay, where exactly particular instruction is going to be terminated on. Okay, 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 students. So this is it for now. So next lecture we'll be discussing about SIP machine pass 1 and pass 2 procedure. Okay. Okay, students. Thank you.